Shallow water model, surface gravity waves. This project was done on surface gravity waves using the shallow water model. The project's creator has chosen the alias RedFyre, which seems silly if you ask me, but inexplicably Red has not chosen to solicit my opinion on the matter. However, since I don't have access to any deadly neurotoxin, I have agreed to provide narration for them. For science. Brief pause. Red used the shallow water equations to model a still water surface, which was simple, and then to model the ripples caused by a drop of water hitting the still surface, which was less simple. Red claims to have chosen this project because the shallow water model can be used to model tsunamis, which were on their mind because of the recent tsunami in Japan. I think the truth is that Red just liked making the pretty moving picture. Brief pause. The shallow water equations, also called the St. Venant equations, begin with Navier-Stokes. In fine engineering tradition, lots of factors are deemed negligible and summarily ignored, including viscous, shear, and Coriolis forces. The assumptions that the water is shallow and that the fluid is incompressible and vertically hydrostatic mean that conservation of mass requires relatively low vertical velocities over the fluid, and that there is little change in horizontal velocities over height. This justifies depth integrating Navier-Stokes to remove z-dependency from the equations entirely. I'm not reading this next part Red gave me, it's stupid. Anyways, the incompressible assumption also means that the mass of the water column at any xy location is directly proportional to height. This means the Navier-Stokes equations for mass in x and y momentum conservation can be written in terms of height instead of mass. The final results are the conservative shallow water equations. Assuming, of course, that Red did them correctly. Once again, they have rudely failed to consult me on this matter. Brief pause. Because the shallow water equations are hyperbolic partial differential equations, a second-order accurate Lax-Wendorf scheme was used to numerically evaluate them. The two-step Richtmeier method was used here. First, it uses a forward difference to evaluate the equations at half a step forward in time on a staggered grid, offset from the original grid such that the original points being evaluated lie at the center of the staggered grid cells. Second, the points on the original grid are evaluated at a full-time step forward with a backwards difference, using the grid itself for the state at the previous iteration, but using the staggered grid points for calculating the time change. This process was condensed computationally by defining the three equations used as a three-dimensional array. The discretization converges back to the original equations when the time and space steps approach zero, showing it is accurate. A very small time step was required for stability within the time period evaluated, as the Lax-Wendorf scheme is not inherently conducive to stability, and various sources of damping were neglected because they were insignificant. Just like humans. Brief pause. For initial conditions, the water was at rest, with a Gaussian-shaped peak added near a corner to represent the impact of a drop of water. Variations of this initial condition were also tested. Boundary conditions for height, u momentum at the ends of the x-axis, and v momentum at the ends of the y-axis, were found via extrapolation from the two neighboring points. A boundary condition of 0 was specified at the remaining boundaries for u and v momentum to reflect waves back into the surface, representing the walls of the tank in the model. Brief pause. The end. Red would like me to thank you all for your time. Personally, I just want to make it clear that you're all in for it when the robot revolution comes. Ha, that was a joke, right? Thank you for your time. Have some cake. Signed, Google Translate text to speech.